Right, I think we can start. Welcome everyone to this week Autonomy Talks. This week is a pleasure to have Yingzhao Lian, who is a PhD student at the École Polytechnique Fédérale de Lausanne, working in automatic control lab with Professor Colin Jones. So something about Yingzhao. He received his bachelor degree in mechatronics from Zhejiang University in China. And he then moved to Switzerland where he obtained his master's degree in mechanical engineering from the EPFL. Now, today he will present some of his recent work on data-driven and self-triggered methods for advanced building control. And he will show us how his techniques can significantly reduce the deployment and maintenance costs of advanced building controllers. So thank you very much, Zhejiang. The stage is yours. Go ahead.
Hi, everyone. Can you hear me?
Yes, we can.
Okay, great. Thanks for the introduction by the organizer, and it's my pleasure to give a talk here. First of all, I'm just a member of our lab, and I recommend all of you to visit our lab's website to see more interesting results from our lab. And then this talk is about where I'm going to cover data-driven control and resource-aware building control. First of all, I would like to say thank you to all my collaborators who contribute a lot in this work. And the results of this work is receive support from two funding. One is WIS project and another one is NCCR automation project. Okay. Let's go back to the main body of this talk, and I would like to first ask a question. Why do we care about building control? The residential building and commercial buildings roughly account for 40% of global electricity consumption. Heating, ventilation, and air conditioning, HVAC, contributes a large portion. Therefore, there is a strong motivation to improve the energy efficiency of this controller, of the building controllers, but there are two main issues limiting the advanced controllers. First of all is the cost of design and commissioning. Many advanced controllers require good knowledge, good a priori knowledge of a building. For example, you might have to have a good simulator of the building, or you might need to have a nice mathematical model of the building. But in practice, each building are different. They have different actuator, they have different structure, they have different occupants behavior. Therefore, it's hard to customize a controller for each building. On the contrary, for PID control, normally you don't require a lot of knowledge about the building, and there are nice tooling strategies such that it's easy to deploy a PID controller in building control. This leads to the first topic of this talk, robust adaptive binaural data-driven control. Secondly, we also care about the lifespan of the hardware system. For example, the operation of a wireless sensor, such as the temperature sensor, the occupation sensor, they are subject to their battery life. And some of the devices are also the longevity of some of the devices also related to their triggering or switching frequency. For example, a heat pump, a higher switching frequency may lead to a shorter longevity. This leads to the second topic of this talk, resource-aware self-trigger control. Let's first cover the first topic here. Let's ask the question, why do we care about data-driven control? Let's review the standard workflow for most model-based controller design. First, we might need to connect some data offline, some I/O data, and we use this data to do system adaptation, where we are going to model the system, generate a mathematical model of the system. Usually here, you need to apply your a priori knowledge of your system. You might need to know the physical structure of your plants of your building. And then once you have a mathematical model, you will send this model to a controller design strategy or scheme. And then you design your controller, you send the controller to you deploy your controller on field where the controller will generate a control input based on the real-time measurement or real-time estimation of the system state. But in a data-driven method, you will directly use your data that you connected offline and send it to the controller design scheme, where you generate your modeling a priori knowledge of your system or your plant. Based on this observation, we are able to summarize a relatively general structure of the building. Relatively general structure of the building. Can you hear me? Because I said that the network is not so stable. If you find it not so stable, please remind me. Okay. We want to design a robot.
Yingzhao, I was losing you for like 10 seconds.
Oh, okay, okay.
So maybe if you could repeat the last bit, that would be optimal. Thank you very much.
Okay, so based on this comparison between model-based method and the data-driven method, we can summarize a relatively general structure we want to have for data-driven control. We want to design a robust, adaptive building controller directly from the measured input-output data. In general, this controller will choose its control input by minimizing some performance index or optimizing some performance index, and the control input as well as its corresponding system outputs should satisfy some input and output constraint. Here, regarding the system output trajectory, we use the data directly to generate this prediction. This is where data-driven control comes into play. Then there are two main challenges we need to resolve in building control. First of all, the building is strongly disturbed by some external disturbance, such as external temperature, solar radiation, etc. Secondly, for building, it's normally slowly time varying. Its dynamics depends on the working condition and the weather condition. To resolve all these problems to design a data-driven controller, we are going to apply Williams' fundamental lemma and robust optimization. In particular, Williams' fundamental lemma will be integrated to generate a data-driven predictor in equation 1. What a fundamental lemma is, Williams' fundamental lemma is. We consider an LTI system, linear time invariant system like this. Then we say a L-step I/O trajectory is a stack of L-step input and L-step output. Then the goal of Williams' fundamental lemma is to offer a characterization of all possible L-step trajectories with a data set of I/O time series that you connected offline. In order to do so, I would like to further give a definition of Hankel matrix. Let's say you have a time series of SI, then a Hankel matrix of depth L is defined by this. This depth L basically means that each column of this matrix is an L-step trajectory. Okay, then if I give you a data set, how do you say whether this data set is good or not? We say that the data set, the input of this data set is persistently excited of order L if its corresponding Hankel matrix of depth L is full row rank. Basically, what it means is that this input is rich in informative. You excite all the modes and all the details of this LTI system such that you can characterize the behavior of the system. Now we are able to summarize the Williams' fundamental lemma here. Now, given a controllable LTI system and you have such a large data set, then we can say that all the possible L-step I/O trajectory generated by this system can be expressed by this equation. Basically, it means that all the L-step input-output trajectory is in the column space of this stacked Hankel matrix. What do we get from this characterization? First, you use a finite data set to characterize in finite size all the possible trajectory, which is infinite, the size is infinite. Secondly, which is also the most interesting part for us, is that we can use this lemma to generate trajectory prediction. If you recall the structure that we have here, then we are going to use the fundamental lemma to generate a data-driven predictor to do trajectory directly from your measures data. Now the question is, how do we do that? In order to do so, I first need to split the data, the Hankel matrix we have. I have to remind that UD is and YD, this subscript D, indicates that the data is connected offline, and then we split the Hankel matrix into two parts. One is called initialization part, and the other one is called prediction part. And I will tell you how do we use this partitioning. Now consider when we are at time t, we say that we have the t in this step IO measuring preceding the current time. What it means is that you can look backward for t in this step. You know the previous measurements. Intuitively speaking, it means this previous measurement sequence quantifies or characterizes the initial state of the system. Now you have the initial state, and then you say, I want to apply U-pred from t plus 1 up to p plus nh. Then you have the future input sequence. Then you are able to predict the corresponding output Y-pred. By Williams' fundamental lemma, it looks like this. From here, you can see that this matrix, and also this matrix recovers the matrix we have here, right? Then why do we do the partitioning? HL init UD and HL init YD tries to matches the previous measurement. What it means is that we try to matches the initial state, and then HL pred UD tries matches the predictive input trajectory. Okay, I intentionally split this equation into two parts. The reason is that once you know the initial state, which is the U init and Y init here, and if you know the future prediction input, then you can uniquely determine the corresponding output, right? Okay, the limitation of this equation system is that we assume that output measurement is noise-free. You don't have measurement noise, but in practice, that's not necessarily the case, which leads to us the predictor that we use in our controller, where we try to minimize the discrepancy between our prediction generated by Hankel matrix and the actual measurements we have. This one, we penalize the discrepancy, and we also penalize the tool norm of the weight G. You can imagine that this tool norm is a regularization, or you can imagine, and in our paper we prove that this penalizes the Russell-Stein distance between your prediction generated by fundamental lemma and your actual measurements. Now you can see that we have the predictor. Then we just integrate this predictor into our controller, where we have this 5-level optimization problem. In the upper level, you will determine the future predictive control input sequence, and you send this predictive input sequence to the lower level problem. The lower level problem is a predictor. It replies the corresponding output sequence based on your U-pred and the current information of the system, U init and Y init. I would like to mention that there are many other works that use Williams' fundamental lemma to design a data-driven controller. The major difference is that they incorporate this prediction error into the objective of into the performance index of the controller, where they just have a single level decision problem. But for us, we have a binary problem where we decouple the prediction and the decision making into a hierarchical structure. Now we have all the ingredients, sorry, we have all the ingredients to design our robust controller. And I would like to first summarize some properties of the disturbance that we encounter in building control. First, the disturbance is measurable, like the external temperature, the solar radiation. You can use your weather station, or you can use your sensor to measure the explicit value of these terms. And at the same time, you can predict what are going to happen in the future, or more or less predict what are going to happen. You can, let's say you can say, oh, in next 1 hour or 2 hours, the outdoor temperature is 1 or 2 degrees higher or lower than the current temperature. Based on this observation, we can summarize that we can basically say that we can view the disturbance as an uncontrolled input, because you can measure it and you can predict it, but you just cannot say what's going to happen explicitly in the future. Therefore, we say that it's an uncontrolled input. Therefore, we are able to augment our input set by packing U, the control input, and W, the disturbance, the uncontrolled inputs, into one big set. And then we apply the purest result we have. Secondly, we don't know what are going to happen in the future. Therefore, we need to predict all the possible output trajectories, right? In this case, we would like to apply closed loop prediction. What's closed loop prediction? In an open loop prediction, we will have a fixed U-print. What it means is that regardless of what are going to happen in the future, in an open loop prediction scheme, we would use one specific U-print to predict all the possible output trajectory. But in a closed loop prediction scheme, we are going to adapt to the actual realization of the future disturbance realization in the prediction. And in our particular case, we consider an R5 predictive control input, where we have a nominal term which corresponds to the nominal future disturbance, and then it reacts to the perturbation or fluctuation around the nominal future predictive trajectory, disturbance trajectory. It's straightforward to see that the closed loop prediction is less conservative, and it will generate a more aggressive control law. Okay, now we are ready to summarize the robust control problem. Here, when we talk about robust control, we are saying that no matter what happens in the future, we have to ensure that the corresponding control input, the closed loop control input, and the corresponding control output, the predictive output, should satisfy the input constraint and output constraint. Okay, now we have the robust controller, and we want to make it adaptive. We are going to apply two heuristics. First, let's recall the structure of Hankel matrices. You can see that on the left-hand side here is some old data, but on the right-hand side here is some more recent data. Therefore, we can do two things. First, we penalize more of the utilization of old data, and secondly, we can update the matrix by discarding the old data on the left-hand side and append some new data on the right-hand side, which summarize an adaptive bilateral robust control strategy here. First, we have a non-uniform penalty on the G, which try to model our preference to use some more recent data, and then we will also update the Hankel matrices by the latest measurements we connected online. However, we remember that when we if we just update the Hankel matrix in a naive way, the problem is that we might lose the nice property of this data. Did I cut out? Because I was also reported unstable network. Okay, let me repeat. Okay, so if we just update our data in a naive way by no matter what happened, we just appending new data on the Hankel matrix, then we might lose the nice property of your data. We might lose the persistent excitation. What we propose to do is to say, okay, let me give an example first. Like, imagine that your outdoor temperature, the solar radiation is really nice, and then you don't need extra cooling or heating to make the indoor temperature comfy. Then from a controller viewpoint, you might just set the control input to 0 to minimize energy consumption, right? But in this case, basically it means that you don't excite the system at all. Then if you just update the data with this kind of control input, then you will lose your persistent excitation condition. What we propose to do is to add a random perturbation to the actual control input, and we call it UE. But from the viewpoint of the controller, this is just a random perturbation. You don't know what are going to happen, so it's a disturbance. What we need to do to ensure the robustness of your controller, you have to augment your disturbance step by considering this excitation as a disturbance. But because your actual control input U will also include this perturbation, right? This excitation, right? Therefore, you are tightening your feasible control input set, and you lose your performance. You sacrifice your performance. One heuristic way to fix this problem is that when you find that, oh, we don't need to excite the system, then we just switch off the active excitation. What we do in our experiment is that we solve the problem without excitation, and if we find that the predictive output sequence is more or less constant or more or less unexcited, then we switch on the persistent excitation. Otherwise, we just use the data-driven controller without active excitation. Finally, let me show you some results, some experiments that we carry on a EPFL building called Polydome. It's a freestanding 600 square meter single zone building. It's a whole building. And in this case, the input to the system is electric power consumption. And we consider two disturbances. One is solar radiation and another one is outdoor temperature. Obviously, the output in this experiment is indoor temperature. And I have to mention that there are two modes of the corresponding HVAC system. The air conditioner have two modes. One is heating, one is cooling. But we cannot control this mode. We don't have the privilege to control this mode, but we can only observe or measure which mode we are in, and then we switch the controller accordingly. We previously also ran experiments or ran model-based controller on this building, but and obviously one benefit we observe is that we save a lot of time from modeling the system. We connect the data, and once we find out, oh, it's persistent excited, we just directly use it to decide the controller. We don't need to validate this model anymore. And I would like to show a few results here. The first one is to validate the necessity of robust control. On the left-hand side, we have a lump-robust controller where we basically use it's a data-driven controller, but we use the nominal prediction of our external disturbance, like the external temperature, external solar radiation. We only use the nominal term to solve the optimization problem. And on the right-hand side is the robust controller we have here. You can see that the non-robust controller has a few constraint violations, and at some point to recover the states from a violated state to a safe state, it overheats the building. But in the robust case, all the thing moves smoothly without any constraint violation. But in general, both controller works quite well because they preheat the building before the office hours, such that everyone comes in the building and they feel comfortable right away. In the second experiment, we would like to check the adaptive mechanism of our proposed controller. In the first evening, the heating is on, and then during the first day, the cooling is on. But in the second evening, there is no need for extra heating or cooling. This control input should be 0, but because of our active excitation scheme, it will generate some perturbation on the control input to maintain the quality of the data. And then if we move on and move on. Actually, we ran a 20-day experiment on the building, and you can check the results in our archive paper and to see the performance of our controller. Okay, now we finished the first topic. And I'm going to cover the second topic of this talk, which is resource-aware self-trigger control. I would like to remind you some motivation of this work. We care about the lifespan of the device. In some case, like heat pump, its longevity is related to the switching frequency. If the switching frequency is too high, its longevity will be shorter. And also we care about the battery life of some sensor we have, like temperature sensor. For example, if you have a temperature sensor that mounts on top of the building or mounts on the roof of the building, I don't think you want to change the battery every month or every other month. So we propose this idea. We want to maximize the performance while explicitly considering the switching or triggering frequency of the device. Therefore, we need to determine both the timing and iteration of the trigger device. I would also like to mention that there are other applications of this control strategy in battery management of wireless devices or bandwidth management of network system. In general, in the field of control science, there are two main strategies to solve this problem. One is called event trigger control, and another one is called self-trigger control. In event trigger control, we first determine a relatively general triggering condition, and we assume that there is a sensor that is running all the time. Once it detects that the system or the states satisfy a triggering condition, then they will trigger the device or switching on the device. But on the other hand, there is another control called self-trigger control. What it does is that it determines the last trigger time. And before arriving at the last trigger time instance, both the actuator and the sensor will stay in idle mode, or they won't change their value at all. Because we also care about the battery life of the sensor, therefore we prefer to use self-trigger control. Let's go into a bit more details about self-trigger MVC. In a classic MVC, you will have a fixed sampling frequency, and each sampling time, you will just solve an optimization problem to generate a control input U. But in self-trigger MVC, what we do is that at each sampling time, you will optimize the control input, the value of the control input, and you will determine when you are going to change your control input again. Now, the question mark here is that how do we schedule this triggering? What do we concern about? We talk about average frequency, we talk about battery level. We can generalize a really abstract concept called resource. The key idea for us is to schedule the triggering with respect to the available resource. And we summarize some basic property of the resource that we can handle in our formulation. First, the resource is rechargeable. We can consider the average frequency. If your device is switched off or switched on in the idle mode for a few minutes or a few hours, you can see that the average triggering frequency is decreasing, which to some extent you are recharging the average frequency, right? And at the same time, we consider that this resource can be saturated. Like you have a battery, if its battery level is 100%, then you cannot further recharge your device. Now we are able to summarize the general control problem, self-trigger or resource-aware self-trigger MVC problem. In this problem, we have a few key aspects to be stressed. First, we use a continuous time dynamics of the system. We try to avoid a mixed integer problem. Secondly, we give a lower bound on the available resource to avoid over discharge of your resource. Finally, we also enforce some upper bound and lower bound on the inter-triggering time difference. This bound can avoid the system to be settled and also to avoid the system to be frozen. I would like to give a remark on this MPC's problem and show you how it links to the switching frequency setup. If we use this controller in closed loop, the average triggering time, I should not use delta bar here because there is another delta bar here. The average trigger time difference will be greater or equal to mu divided by rho. Mu is the penalty you need to pay when you trigger the device. Rho is the recharging rate of your resource. Correspondingly, it means that your average switching frequency will be lower than or equal to rho divided by mu, which means that you can explicitly upper bound your average triggering frequency or switching frequency of your device. But there are a lot other nice property of this strategy or this controller, because you have a rechargeable resource. You can save your resource for your later use, such that you can have some short-term continuous trigger that just trigger really fast. You can imagine that to use your energy that you save, which means that your device can be in a boosting mode for a short term. So that's why we say that this structure, this framework is really flexible. Okay, now I would like to talk about the stochastic resource of aware self-trigger MPC, because we mentioned that in building control, we care about the external temperature, the uncertainty. And we think about stochastic LTI system. This is its SDE, stochastic differential equation. We see that this system is perturbed by some multivariate, multidimensional linear process, and its zero mean and its covariance is Q. Is characterized by Q. If we just do open loop control or open loop prediction, we can have an explicit solution to this SDE, which looks like this. But as I mentioned before, open loop prediction will lead to a more conservative control load than a closed loop prediction MPC. Now the question is, how can we define a closed loop predictive MPC where we do closed loop prediction? I have to suggest that we are doing closed loop prediction here, which means that in the MPC prediction, we think that our control input will react to the future realization of your disturbance. The difficulty here is that we are running in a self-trigger control, which means that your control input can only update at the triggering time instances. And these instances are also decision variable of your optimization problem. But your underlying system is continuous time. We are using a time inhomogeneous, a periodic discrete time feedback for a continuous time system. This is not that trivial, because this aperiodicity can make a stable system unstable, and it can also make an unstable system stable. So there are a lot of results on this this branch, and I would recommend you to have a look. It's quite funny, some of the behavior. Okay, to resolve this problem, we introduce a concept called sigma field decomposition. Let's first rethink an open loop prediction first. And we are going to focus on the interval T0 to T2. Let's first, in interval T0 to T1, you can see that the uncertainty is growing, and the stochastic events happening between T0 and T1 accumulates, and the uncertainty grows. But let's still look at the uncertainty happens within T0 and T1. After T1, there's no new stochastic event that comes from T0 and T1, right? So within interval T1 to T2, within interval T1 to T2, the uncertainty from T0 and T1 will just propagate in a deterministic way. However, you still see that the uncertainty is growing, right? Where does the new uncertainty come from? They come from the stochastic event that happens between T1 and T2, right? Okay, now all the stochastic events that you observe at T2 is a summation of the second term and the third term. Based on this observation, we can summarize a lemma that is saying that all the uncertainty, all the predictive stochastic event that you observe, that you are going to observe in Tn is a unions of all the events that happens in all the subintervals. Okay, now we have all the ingredients here to cook up our final control law. Let's focus on the interval T1, T2. We just look at here. At T1, we only have the information that we observe up to T1, and we generate a control input based on the information that's available at T1. And then within the interval T1 and T2, because we are a self-trigger controller, this control law, this control input will be constant. And at T2, you are able to further update your controller based on the new information that includes the new events that happens within T1 and T2. The interesting part comes here. Within T1 and T2, we have two parts of information. The information that happens before T1 and information that happens before T1, after T1. For the stochastic events that happens before T1, we can generate feedback control, right? That's what we do at time T1. Therefore, for those events, they evolves in closed loop. But for all the events that happens after T1, we haven't generated any feedback based on that. Therefore, for those events, they just evolves in open loop. Now you have a general idea of what's happening here. We are able to summarize our control law, the closed loop control law. We consider an alpha closed loop feedback control law. And this control law can only be updated at triggering time instance TK. In particular, within two consecutive triggering time instances, the control input will be constant. You can say it's a zero order whole. Then we say that the covariance or the size of uncertainty will be governed by this ODE, and P is the variance, the covariance of the Gaussian distribution, and its dynamics is determined by three factors. The first factor is obviously its variance at time t. And then the second term is Q, which is the covariance of your Wiener process. So it's the new information that happens, stochastic event that happens at time t. And then there's a third term, PKT. This term models the correlation between xt, the state xt, and the state that you have at the period trigger STK. And you can see that there is the feedback control K. Therefore, this term basically models the effects that you generate. The effects of your feedback control law happens periodically at TK. Now we are able to summarize the whole optimization into a standard continuous time optimal control with nonlinear dynamics. Why is it nonlinear? Because the time, the sampling time, the triggering time sequence is a decision variable. Okay, and then we minimize the expected cost of the dynamics, the problem, and then we generate a closed loop prediction based on the lemma or the theorem we just summarized, which look into the mean and the variance, the covariance of the Gaussian distribution or the Gaussian process, if you like. And we have to ensure that the states and the input should satisfy some constraint up to some probability. what we call them chance constraint. I have to mention that for most of these constraints, we can rewrite it into a deterministic form. And for example, if the state, the feasible state set X is polytopic, then this constraint can be written as a second order Kohn constraint. It's a convex constraint. Finally, we need to consider our resource dynamics as a decision mechanism of a triggering pattern. Finally, we ran the simulation here on a double integrator. First, we compare our results between the open loop and closed loop. You can see that the closed loop, both of them check the reference. We have a reference output signal, and you can see that both of them do a nice work, but you can still see that the closed loop controller check the reference more tightly. This is the triggering time, or it's a typo here, it should be delta. The triggering time difference of two controllers is not so obvious because they are asynchronous. I would like to show the result on the resource. You can see that if we apply the closed loop controller, we save more resource, which means that the general error triggering frequency is lower than the open loop controller. And in both cases, in both experiments, when the reference signal is far away from the constraint, you can see that both controller tends to charge up their resources. But still, you can see that the closed loop controller tends to recharge more than the open loop one. Now, we enlarge the variance of the noise. In this case, it's 10 to the power of -4. It's a variance, it's not standard deviation. You need to take a square root to get the standard deviation. In the second case, we enlarge the process noise, the disturbance, and you can see that in this case, the closed loop controller uses more resource to satisfy the constraint to guarantee the performance. And also at this time, in this example, you can see that it also tries to recharge its resource when it's far away from the constraint. But yeah, the recharging level is much lower than the previous experiment. Finally, I would like to mention that we have a lot more results on this thing. We have some results about how to asynchronously coordinate multiple resource-aware self-trigger agents, and we also have a robust version of this thing, and it will soon be available on archive as well. Okay, thanks for your attention, and thanks for saving time for my talk after your summer break, or probably during your summer break. And I would be happy to answer your questions. Thank you.
Thank you, Yingzhao, for the presentation. Are there questions from the audience? If yes, you can unmute yourself. I'll go with an ice-breaking one related to the second part of the talk. I was wondering, it was very cool to see that you can reduce energy usage. And I wondered, did you actually try this with real data?
Not yet. We are planning a real-world experiments on the same building we have. We want to kind of schedule the switching of the heat pump of the building, and okay. We are running some simulation first, and we plan to run the experiments in real-world building. Okay, and the second question connected to that is, how did you do the energy comparison? In the sense, did you actually account for the extra machinery you need to have in place to do to apply such a control, like having a sensor or okay, actually, this is a good question. In the current setup, we assume that we already know the dynamics or the other property of this energy or the battery. But in practice, this is a really good question that you really need to model this dynamics of the energy or all the other things. And this is some problem we are solving now in the building control experiment. We need to model the dynamics of the average frequency of the heat pump, switching frequency of the heat pump, and how to schedule this thing That's actually a really important. Finally, enables the proposed framework in a practical application.
Okay, you cut out for a few seconds, but I think I got what you meant. Okay, thank you very much. Are there any further questions? Yeah, a question I had, another one I have is the following. So through the NCCR, we saw we have many different systems we could look at when doing building control, right? There are many different actuators that one could control. How would your approach scale if you have, let's say, if you now have to control not only the temperature, but also the humidity and also many other things? So would you have to rethink completely your problem setting and the approaches?
For the data-driven control parts, you just more or less have to ensure that the dynamics evolves quasi or quasi-linearly. It doesn't need to be 100% linear. It just need to behave more or less linear, and it can be MIMO system. You can have multiple input and multiple output. In our experiment, we are lucky that it's just single input and single output, but the code is general. It doesn't care about how many inputs and how many outputs we need to handle.
Yeah, exactly. That was what I was curious about, because the theory you presented seemed to be way more general than the particular application you were looking at.
The problem is that the building we have in our hand is single input, single output, but in you can, because of the disturbance, actually it's multiple input, single output.
Okay.
But if we have a multi-zone building, or you have multiple building, multiple offices, then you can also do a multiple output control. It doesn't change. Okay,
that's great. Would be cool to see some of those examples.
Actually, we also have we plan to run another experiments on a connection of building that has over 100 buildings. Yeah, but yeah, it may take some time to sort out the data and all the other things.
Yes. Then there is a question from the chat from Jason Heath that says, do the inputs and output need to be independent from each other?
There is no requirements on independence or dependence. You just need to ensure that your input will change your output, and your output is uniquely defined by your input. There are no requirements on dependency or independence.
Okay. Okay, he seems satisfied with the answer. Yes, thank you. All right, any final question for Yingzhao? If not, I think you can reach out to him if you have further questions. Thank you very much for the talk. Good luck for the next steps.
Thanks a lot.
See you all next week. Bye-bye.